Freebody diagrams. So overall, the way this test, the scores went, was kind of like there was a big chunk of the class that did well. The direction is going well. But then there was sort of like a split. And this has happened in this class before, where some people are just currently not sort of in the boat. And so this is sort of like a critical time to make sure that this stuff makes sense. This is the most important topic in the class. So I want to go through how to do this test, try to point out the things that people look like they might have been misunderstanding. And then if you're not happy with your score, compare my solution to the way you did it. Find the things that went wrong, you know, not just now, but maybe like later at home or whatever. And come talk to me, you know, either at office hours or make an appointment over email, and I'd be happy to talk about it. You know, like one bad test doesn't have to affect your grade at all because the final can replace the score. But the key thing is to get back on track so that your future scores are good. Let me go through the solution, and then when I'm done with this, I'll get back to internal loads. Yeah. No, you totally should get one, but I'm still not giving you one because puppies are expensive. Okay. So yeah, sorry about that. Okay, so exam 3. Number 1. So this one looked like this. You had a roller over here that was connected to a beam, and then there was a beam like that, and a beam like that, and all of these are connected by pin joints. And then one like that, and that, and then this pin joint is connected to the wall. There's an external force of F applied there. And I numbered the members so that they would match for everybody. 1, 2, 3, 4, 5. Oh, one other thing I should say about this is when I graded this, I just looked for, you know, I always say that the way I approach these joints is I lump the joint in with the lowest numbered member. That's just a bookkeeping thing. There's no reason you have to do it that way. That's how I graded it. So if you used a different sort of bookkeeping strategy and you lumped the joints in with something other than the lowest numbered member, that can still be right, and I marked it wrong. So if you think that happened, definitely come talk to me and explain to me how you did it, and I'd be happy to give you those points back. I graded it as if the joints were going to be part of the lowest numbered member at every joint. Okay, so free-body diagram for body 1. And as I do this, I'm going to draw the side views too to just sort of clarify the way to think about this. Okay, so body 1 is that. And since 1 is the lowest numbered member in the whole thing, we're assuming that any joint that's attached to member 1 is part of member 1. So you can think of this as having this roller as part of it. okay? You're lumping that in with member 1. And so what's going on down here? Let me name these joints too. I'll call this A, B, C, D. And let's draw a side view of joint A. So if I was looking from the, I don't know, let's say from the right side, here's what I would see. I would see member 1 over here going off, well, I guess coming diagonally towards me as you get higher. So there's member 1. And I would see member 2 coming horizontally towards me. Stop me or ask me to clarify if something's hard to understand. And then you would see that roller that would look something like this, you know. And then a pin connecting all of them. Okay, so this is member 1, member 2. This is the roller. And now I'm going to associate the joint, which is the pin and the roller. I'm going to associate that with member 1. So everything that's shaded, I'm going to say is part of member 1. Okay. And so now you can see that if everything that's shaded is part of member 1, we have a force vector applied to 1 by 2. So that's F12. The roller is part of 1, so there's no force between the roller and 1, but the ground is pushing up on the roller. So on member 1, you also have this force, I'll call that RA, and it has a known direction because it's a force on a roller. Okay. And then at joint B, what do you see there? If we're looking from the right side again, you see member 1 going diagonally away from you as you go down. You see member 3 coming diagonally towards you as you go down. And you see member 4 coming towards you. And those are all connected by a pin. We're going to associate everything that's shaded is part of member 1. So that's member 1, and then the pin is member 1. Okay, so now up at joint B, what's in contact with member 1? What's in contact with the shaded stuff? The shaded stuff is touching member 3 and member 4. So here we have a force vector on 1 by 3 and a force vector on 1 by 4. And you can see how drawing that side view, if you get confused, can help you clarify what's touching what. By the way, two things that came up a few times that I didn't take points off for, but really, well, one is kind of just a detail type thing, and the other one is really technically wrong, but I didn't take points off. But you need to be clear about this, is first of all, this is an engineering class and you're trying to get ready to work as engineers. And a big part of engineering is conveying these ideas to other people you're working with. There aren't really engineers that just sit in a room by themselves and do engineering. Well, there probably are, but not most. And so you need to be able to convey these ideas. And part of conveying those ideas is differentiating between different types of variables. This is a scalar variable. It doesn't have a vector symbol. These are vector variables, and so you should use those vector symbols. I can't imagine ever taking off points for that, but I can imagine getting more and more annoyed with each exam as you continue to not do that. So if you care about my feelings, we'll use it. And then the other one this is maybe more important. This is technically wrong if you don't do this. Is when you draw the directions of these unit vectors, what you're doing is saying what a positive value is that's associated with that variable. So if you draw, say, your F14, you draw a unit vector that way and a unit vector that way. What you're saying is if you get positive values for those vector components are going this way and that way. Or in other words, what you're saying is a positive value of 3 and a positive value of 4 for those components, for those variables. When you plug it into Newton's second law, you'd write that as -3, -4. Okay, so you do not want to go down that road. Okay, so those should be given in the positive directions. Yep.
For the reaction forces that have two directions, or it's an unknown force, is that a vector or is that a scalar?
If you know the direction, it's a scalar, and if you don't know the direction, it's a vector. All right, so now we're going to number 2. Any questions on that one? Any questions about, like, anyone want clarification on the relationship between this side view and what's on the free body diagram? Okay, so now number 2. So member 2 is horizontal, and it goes from joint A to joint C. So I'm going to draw a side view of joint C. And if you look at joint C from the right, you see member 3 going up diagonally away from you. You see member 2 going horizontally away from you. And you see member 5 coming diagonally towards you. And a pin connecting all of them. And then there's one more thing going on at this joint. There's an external force applied. So that force F, we're going to treat as being applied at the pin. So that force F is there. Okay. The lowest numbered member at that joint is 2. So everything that I shade, we're going to treat as if it's part of 2. So that's 2 and the pin. Okay, so at C, at the right side of this body, what's touching 2? Well, there's the downward force F, because that's touching the shaded part. And then 3 is touching it and 5 is touching it. So there's the force on 2 by 3 and the force on 2 by 5. And now we'll go back to the other joint, joint A. We already drew that side view. Okay, so now we're asking ourselves what's touching 2. Well, the pin is touching 2, and the pin is member 1. So there's a force on 2 by 1, or a negative force on 1 by 2. But that roller is not touching 2. And so the ground is not touching 2. Okay? And so we don't have that force RA touching 2. We only have this force over here, negative F12. Okay? And so if you put in that upward force RA, when you do this calculation, your answers are going to be wrong, because you will have double counted that reaction. Any questions about that one? So now free body diagram of 3. That's this one. And it's going between joints B and C. I've already drawn both of those side views, so let's look at the side view for B first. And we're looking for what members are touching member 3. Well, member 3 is touching the pin, which is part of member 1, so there's definitely a force on 3 by 1, or negative force on 1 by 3. But 3 and 4 are not touching each other. Each one of those is touching the pin, but not each other. So up here, the only force you have is the force on 3 by 1, or negative F13. And then down at the other joint, that other joint is C. What's touching member 3? That force F is not applied to member 3. It's applied to the pin, member 2. 3 is touching 2, so there's going to be a negative F23. 3 and 5 aren't touching each other, and it doesn't have anything to do with the order that I drew those things. Those just are not touching each other. Even if they're next to each other, they're not touching each other. So the only force found at the other end is the force on 3 by 2, or negative F23. So now the free body diagram of 4. 4 is the horizontal one at the top. So 4 is going from B to D. So first let's look at joint B. What's touching 4? 4 is touching 1 because it's touching the pin, but 4 is not touching 3. So all there is here at joint B is a force on 4 by 1, or negative F14. And now we'll go to joint D at the other side of member 4. We have member 4 going horizontally away from us, member 5 going diagonally away from us. So at the joint D, we have 4, 5, and then we have the ground. I don't know how you want to draw that, but I'll just put it in as a pin. So this is 5. Okay, so 4 let me write it like this. So there's 4 and 5. We're going to treat the pin like it's part of 4. Okay, so touching member 4. 4 is touching 5. So over here there's a force vector F on 4 by 5. And then 4 is also touching the ground. So we also have this force, call it RD or something, that reaction force. And that's all. Any questions about that one? And then the last one, Freebody diagram of member 5. That's like this. At the bottom left, it's a joint C. At the upper right, it's a joint D. So let's first look at what's touching member 5 at joint C. That force F is not applied to 5. That's applied to 2. Member 2 is touching 5, but member 3 isn't. So the only thing touching 5 is member 2. So we have the force on 5 by 2, or negative F25. And that's all. And then at the other end, we have the joint D. At joint D, right here, what's touching member 5? The ground is not touching it. The ground is touching member 4. It's touching the pin, which is part of member 4. So the only thing touching 5 is 4. So we have negative force on 4 by 5. That's it. So if you ever get confused about this stuff, sometimes I know for me too, it gets confusing just drawing the free body diagrams. But if you get confused, draw a side view of the joint and that can clear it up. Okay? And if you have trouble understanding what I'm talking about there, come talk to me and maybe I can help you with it one-on-one. Any questions about number 1? Okay, now number 2, I'm going to just draw the free body diagrams and leave the calculations out of it. But this one looks like this. There's a pin joint over here connected to the wall. And a member like that with a pin joint here connected to a vertical member. And the vertical member is connected to the ground down here. And then in the middle, there's a 500 Newton force. And up here, there's a 200 Newton force. And people numbered these either way. I'm going to do it with this number 1 and this number 2. So a free body diagram of 1. You have in the middle the force on 1 by 2. You have the applied force of 200 newtons at the top. And down at the bottom, you have the reaction load. I'll call that RA. And then member 2. At the contact with member 1 on the left side, you have the negative force on 1 by 2. you have the downward force of 500 in the middle. And then at the right end, you have a reaction force. I'll call that RB. And so for variables, you have RA, F12, and RB. So that's 6 variables. You'll get 3 equations from Newton's laws for each one of those members. So 6 equations, and you can solve. Any questions about that one? Okay. So now we're going to go back to internal loads. And ask yourself this. So in the examples and the problems that you've done so far with internal loads, why haven't we done anything with weight yet? So why have we neglected the weight in every internal loads problem so far? Well, it turns out that weight isn't really a point force applied at the center of mass. It's really a distributed load. So for example, if you have a problem like this, so here's a wall, and then you have a cantilever beam connected to it, and the mass of this beam is 100 kilograms. And let's say that the length is 3 meters. Then the loads on this beam are really, so if the mass is 100 kilograms, then the weight, mg, is that times 9.81, so 981 newtons. And so the free body diagram has the external loads from the fixed joint, I'll call that the force RA, and the couple MR. Okay. And then it's a uniform distributed load. And the magnitude of this distributed load is the total weight divided by the length. So that's 981 thirds, divided by the length, newtons per meter. But if we are doing this problem just to calculate those external loads, we've done a ton of problems like that. That's a pretty easy problem compared to rigid body problems we've done so far. And we know that the way we do it is instead of writing the weight as a distributed load, we write it as a total force of 981 just acting at the center of mass. Okay. Well, we do that because that's the only way we have to do this calculation. But now the question is, when can you make the jump from something that's a distributed load to treating it like it's a point force? That's sort of the key thing here. Because if you did this calculation assuming that that weight was a point force acting in the middle and did your internal loads based on that, you get the wrong answers. So the key thing is you need to represent distributed loads as point forces to do the calculations. But you can't do it, switch from a distributed load to a point force until you've chosen the body to isolate. Okay, so if I go back to that example, once I draw a free body diagram of the whole thing, I've chosen the body that I'm isolating. And now I can say, so I have this force RA and this couple MR. And now that I've chosen the body to isolate, now I can treat that distributed load like it's a point force. And now we have this downward force of 981. And this problem gets pretty easy. RAX, RAY plus 0, negative 981 is equal to zeros. And so this function, this force RA is equal to 0, positive 981. And then the moment equation, I'll use this as the about point. So we have MR, there's no moment from the RA, and then there's a negative moment with a moment arm of 1.5 times 981 is equal to 0. So MR is equal to 1471.5 Newton meters. Now I'm going to do the cut for the internal loads. And once I do the cut, I'm going to be choosing a new body to isolate. And so I have to, all over again, take the distributed load and represent that as its own point force on that isolated body. Okay, so cut 1. So now I think that, so what are the places where the internal load subfunctions can change? Did we talk about that? Yeah. So how do you know when to change to a different cut. So you look at places where you look at the endpoints, and then you look for places where there are point loads, or places where the function describing the distributed load changes. For this problem, the distributed load is the same over the whole thing, okay? And so this cut represents all x's between 0 and 3. So I'm going to take some representative piece, and I'm going to ignore all the rest of this. And over here we have, I'll just draw it as an upward force. Now we know that all we have here is an upward force of 981 and a couple of 1471.5. And then the other load acting is a distributed load. Okay, we can't treat it anymore like it's a point force in the middle. That was for a different thing that we were isolating. So this distributed load goes over the whole length. Right, there's the distributed load. We're neglecting a whole bunch of that weight. All of that distributed load that's shown in light blue is stuff that isn't acting on our isolated piece. Okay. We do know that the magnitude of this distributed load is 981 thirds. Let's see, what's that? 981 thirds. So 29, 294.3. That's the magnitude of that distributed load. And then we have these internal loads, T, V, and M. We knew the total weight was 981, and the total length was 3 meters. And so the distributed load is just the total weight divided by the length. What? Oh, okay, thank you. 327 point what? Okay. And then what's the length of this piece that we isolated? X, yep. Well, we can't do this calculation with this distributed load represented like that. So now that we've chosen the body to isolate, now we want to represent that as a point force. Okay. So now we want to represent the distributed load as a point force. So let's think about this distributed load. We have a height of 327 for this rectangular shape. What's the width of this rectangle? X. And so what's the total area of that rectangle? 327x, yep. And the centroid is right in the middle. So how far is the centroid from either end? X over 2. Now I'll try this free body diagram again. We have an upward force of 981, couple of 1471.5, And now we have a downward force in the middle of 327x, and then the internal loads. And the distance from that 981 to the 327x is x over 2. And the distance from the 981 to the t, v, and m is x. Yep. Yes, that's right. Newton's law says 0, 981. Plus 0, negative 327x plus t negative v is equal to zeros. And so we get the t is equal to 0. And v, this is the first time we've seen v have x explicitly in the function. V is equal to negative 327x plus 981. And now the moment equation, do it the same as we did before. So the about point's at the left end. We have the moment of 1471.5. And then a clockwise moment, so minus moment arm of x over 2 times a force of 327x. And then plus m minus vx, like we always do, is equal to 0. So m is equal to positive vx plus 163.5x squared minus 1471.5. Yeah. So remember the way we always have done distributed loads when we calculate external forces is to replace that by a point force. The magnitude of the force is the area. And the area was that times that. And then the location is the centroid of the shape. And the centroid is, since the whole length is x over 2 from this end or that end. So if we have a triangular distributed load, it's not going to be right in the middle. It's always going to depend on the centroid. And now we can replace v with this above. So m is equal to negative 327x squared plus 981x plus 163.5x squared minus 1471.5. And if you lump the two x squared terms together, you get that m is equal to negative 163.5x squared plus 981x minus 1471.5. Okay, here's something. I'll give you a list of all the things you can do to troubleshoot your answers. But this is kind of surprising, but very useful. Let's let Q of X represent the magnitude of the distributed load of the downward, let's say, of the downward distributed force at any value of X. Okay, so you could have more complicated distributed loads. This is like as simple as it can get. But our distributed load just has a magnitude, whatever the X value is, it has a magnitude of 327. So for us, the function Q of X, and it's downward, so it's positive. So for us, the function Q of X is just 327. Okay, so first of all, for any X value, it has to be the case that the derivative of the bending moment function with respect to X is equal to the shear force. So let's check that out. dm dx is equal to negative 327x plus 981 minus 0, and that matches the shear force. And also, the derivative of the shear force function with respect to x has to be equal to negative q of x. So if we take the x derivative of the shear force function, we get negative 327. The negative of that is positive 327, and 327 was our distributed load function. These are helpful for finding errors. Okay. Yes. Yeah. So here's our shear force function. Take the derivative of that with respect to x, you get negative 327. Take the negative of that, which gives you positive 327. And 327 is our function q. Let me do another example. And this time we'll use a triangular distributed load. So let's say we have a pin joint at the right and a roller at the left. And a triangular distributed load with a maximum value at the right end of 10,000 newtons per meter. And let's say the length of this is 2 meters. and we want to calculate the internal loads. Well, you're always going to want to calculate that function q. So for this, how would you calculate the function q? So q of x is the equation for this line. Okay, so q of x is equal to mx plus b. We're just going to use, the equation for a line. When x is equal to 0, what's the y-intercept? What's the height of that distributed load when x is equal to 0? 0, yep. So this goes away. That won't always be the case, but a lot of times it will. And then how do we figure out the slope? Rise over run, yep. So over a run of 2 meters, it has a rise of positive 10,000. So m is equal to rise over run, which is 10,000 divided by 2. And so q of x is just equal to 5,000x. Okay, so the first thing we have to do is calculate those external loads. A free body diagram of the whole thing. We have a roller at the left, so that's a force with a upward direction. I'll call that RA. And then at the right, it's a pin joint, so that's call that RB. That's an unknown vector. And now that we've chosen the body to isolate, we can represent that distributed load as a point force. This is the stuff that we did with rigid body, calculating the external loads. We have a triangle with a height over here of 10,000, width of 2. So the area is 2 times 10,000 over 2, or 10,000. And the centroid is 2/3 of the way from the point towards the wall. So 2/3 of 2. And so we have a downward force of 10,000. And this distance is 4/3. Newton's second law says 0 RA plus 0 negative 10,000 plus RBX RBY is zeros. So we can tell right away that RBX is 0. But we can't solve for these yet. We have RA plus RBY is equal to positive 10,000. I'll just set that aside for now. And then the moment equation. if the about point is here, we have a moment arm of 4/3 and a force of 10,000, and that's a clockwise moment, so negative 4/3 times 10,000. And then we have a moment arm of 2 and a force of RBY, and that's a counterclockwise moment, so that's positive, is equal to 0. So you can solve this and you get that RBY is equal to, I think that's 6666.6 repeating. And so that tells us that RA is 3333.3 repeating. Okay, so now we have our external loads. I'm going to redraw the free body diagram with what we know. So we have a upward force of 3333. And on the other end, we have an upward force of 6666.6. And then we have this distributed load. With a maximum height of 10,000 newtons per meter, or the other way to represent that is we have this distributed load function of 5,000x. Okay, so now we have to think about how many cuts we have to make. We have 2 endpoints. Is there any place between the endpoints where the function representing the distributed load changes? Nope, that function is 5,000x the whole way. So all we have are the endpoints, and so we only need 1 cut. Okay, so cut 1 represents x values between 0 and 2. So we'll isolate a piece like this and ignore all this. Okay. And we have a deal kind of like this. We have an upward force here of 3333. Okay. Over here, off of the body that we're isolating, there's a distributed load of 10,000 newtons per meter. But this doesn't have any relationship to the body that we're isolating anymore. You know, this is acting on something else. We're isolating this, and this has some lower value. So we need a way, in order to calculate, what we want to do is represent this distributed load as a point force, right? But to do that, we need to be able to calculate this area and calculate the centroid, okay? So we know that this distance is x, like it always is. And let me draw the internal loads like we always have them. Okay, so I'm going to draw the triangle that we're isolating over here to figure out how to treat this as a point force. We have a width of this triangle, a base of x. What's the height of this triangle? Less than 10,000. It's not 10,000 because this triangle is just the black triangle. Okay? It's not any of this. This point is 10,000, but this, the way I've drawn it, is 4,000 something or whatever. And if x changes, that value changes. So the height of this triangle is going to have to depend on x in some way. So can you think of what that height is for a given x? 5,000x, that's right. It comes from Q. And so the area of this triangle is x times 5,000x over 2, or 2,500x squared. And the centroid of this triangle is here. What's this distance? 2/3 x, yep. And so now we can represent that piece of the beam with the force of 3,333 and the internal loads T, V, and M, and then a downward force of 2,500 x squared. That's a distance of 2x over 3 from the left end. And now that we've represented the distributed load as a point force, now we can go to Newton's laws. So Newton's second law says 0, 3, 3, 3, 3, plus the easiest way to not get confused about the signs and stuff is to think of this number as the magnitude. This is a unit vector in the negative y direction. So this is 2,500x squared times 0, negative 1. So that force vector is 0, negative 2,500x squared. Plus t negative v is equal to zeros. So there's no tension. And the shear force is equal to negative 2,500x squared plus 3,333. And then the moment equation with the left is the about point. That force of 2,500x squared has a moment arm of 2x over 3. So 2x over 3 times 2,500x squared. And is that a clockwise or counterclockwise moment? Clockwise, so that's negative. And then plus m minus vx is equal to 0. So m is equal to positive vx minus 1666.6 repeating x cubed. And so m is equal to, yes, thanks. So m is equal to negative 2,500x squared. Nope. So we're going v times x. So v is equal to negative 2,500x squared, and then we multiply that by x. So negative 2,500x cubed plus 3,333. I stopped writing the 3 repeating, but that's still there. Times x. plus 1666.6 repeating x cubed. And we can combine those two x cubed terms. So m is equal to, I think that's negative 833.3 repeating x cubed plus 3333.3 repeating x. And there's a lot of little places you can make mistakes, but now we can check this with the derivative relationships. Dm dx is equal to negative 2500 x squared plus 3333.3. That should be equal to v of x, and it is. So that one works. And then dv dx is equal to negative 5000x plus 0. And that's negative q of x. So that one holds. Yeah. Yes. Yeah, that's a really good question. So why, if we know the relationship between, if we know there's just like, so right at the start, we can get that function q of x. Why don't we just integrate from there to get v of x, and then integrate from there to get the bending moment? And you're right, the problem is that we would have to come up with those constants of integration, which wouldn't really be that much harder than doing what we're doing, but it's not any easier either. So you could go that way, but we're going this way. Any other questions about that? Okay, so the last thing I want to do is give you a set of, a complete set of checks on your answers. The first two are the ones that I just mentioned. So dm dx is equal to v. dv dx is equal to negative q. The third one is the internal tension is equal to 0 at an endpoint if and only if, have you seen that notation in math? If and only if. There's no horizontal point force at that endpoint. So the only way that you can have a non-zero internal tension at an endpoint is if there's a horizontal point force at that endpoint. Otherwise, it has to be 0. That horizontal point force can come from some applied external load, or it can come from a reaction load, but there has to be a horizontal point force. And it can't be a distributed load, it has to be a point force. And then we have versions of these for all of the internal loads. So V is equal to 0 at an endpoint. if and only if, what do you think this one is? There's no vertical point force at the endpoint. Does that sort of make sense? Point force at that. So these are ways to identify if you're going to have, so a lot of times at the endpoints you're going to have 0 values for these internal loads, and this is how to know if that should be the case. Yep. Either one, either endpoint. And then the last one is bending moment. So the bending moment is equal to 0 at an endpoint if and only if, what do you think this is? There's no point yes. If and only if there's no point couple at that endpoint. Usually, I mean, when I do internal loads calculations, I always check these derivatives. I can't say I very often check these other ones, but sometimes, if nothing else, it's a way to sort of help you graph out those functions if you're trying to graph those functions. If you can see that if there's no, say, for example, at the right endpoint, there's no vertical point force, then you know that your shear force function has to end up at 0 at that endpoint, that kind of thing. I always do these anyways. The rest you can use at your discretion. But when all this stuff is like super quizzy, so whether you use it or not, you should try to remember this stuff for the quiz. Okay. Any questions? Okay. Have a good weekend.